In this video, I'm going to introduce the Matlab debugger. A debugger is a program that allows you to run another program under the control of the debugger and to examine the execution of that program. Just for clarity, from now on when I say program, I'll mean the program that you want to look at, not the debugger. Most debuggers have similar features, which include the ability to stop the program at any point you choose, to examine the current values of the variables, to print a traceback listing, that is a list of the functions that have been called to get you to this point in the execution, and even to step up out of the current function to the calling function, and to examine the variable in the calling function's workspace. Matlab's debugger has all of these features. Most can be accessed using the Matlab editor as a graphical user interface, or using the command window and typing the appropriate commands. Almost all of the debugger commands begin with db, for instance, db step to take a single step in the code, db cont to continue running the code, etc. I'm going to introduce the features of the Matlab debugger using two examples. For the first example, I've intentionally introduced a bug in my quadsimp program. The new version is called quadsimp1, and it calls simp1 to implement Simpson's rule. Hopefully you remember that quadsimp uses Richardson extrapolation together with Simpson's rule to estimate an integral to within a given tolerance. Before I look for the bug in quadsimp1, let's see how quadsimp works, that is how the correct version works. So here I'm asking quadsimp to integrate sine from 0 to pi over 2, and I'm asking it to do it very accurately with a tolerance of only 10 to the minus 10. I know the exact value of this integral is 1, so I can check the answer. It's as accurate as it can be. In this case, the error is only at the round-off level. Now I can watch quadsimp execute by using the debugger. I begin by setting a breakpoint in quadsimp. Command is db stop, and I have to give the name of the program. This will set a breakpoint at the first executable line in the function. Now I'll execute the program again. Now you notice that Matlab automatically brings up quadsimp.m in the Matlab editor. You notice this green arrow here which shows where the execution stopped. And you notice this red dot here which indicates that a breakpoint has been set. Now what can I do at this point? Well, I can go to the command window and I notice the prompt has changed. It now has this K before the usual prompt symbol. If I type whos, I will see that I'm in the function. The variables in the workspace are f, a, b, and tol. I could look at their values. F is a handle to the sine function, and a, b, and tol have the expected values. Let me note that it's possible to look at the values of the variables within the editor. In fact, if I just put my cursor on top of one of the variables that's been defined, I can see the values. On the other hand, if I put my cursor on top of a variable that's not yet been defined, it does not show the value. And actually, you learned something from this. That green arrow is pointing at the line that's about to execute, not the line that has executed. Next, let me show you how to execute one line of code. There are two ways to do this. First of all, in the command window, if I type db step, that takes one step. And if you happen to notice over here, the green arrow did advance by one line. And if I were to put my cursor on N1, it now has a value because that line of code has executed. Another way to do this is to click on this icon here, the step icon. That also advances the line by one code. Now notice that I1 has a value. I do it again, N2, and one more time. Now I2 has a value. Before I go on, I need to point out that this trick of hovering to observe the value of a variable only works if it's turned on. To turn this on, you have to go to the Preferences menu, and you go to the Editor Debugger, and to the Display. And these are called data tips. You need to enable data tips in edit mode. So I had that checked, so it was enabled. By default, it's not enabled, at least on my system, so you might have to go into the Preferences and enable data tips in edit mode in order to use this. What else can I do? Well, let's take a few more steps. And now I'm about to execute this line. Notice that this line involves executing another function. If I do a step, that function executes. I2 does have a new value now. And then the loop will continue. I suppose now I want to observe the execution of that function simp. There are two ways to do this. First of all, in the command window, if I type db step in, that will cause the debugger to step into the simp function. I can do the same thing with this icon. Notice it says step in. So when I step in, I go to the first line of executable code in the function simp. And then I could step through here if I wanted to. I want to look at the value of n. It's 16, so that's not too high. But notice that I'm coming up to a for loop. Now suppose I want to execute that for loop all at once and I don't want to step through it, observing each iteration of the loop. What I can do is go here, click to put a breakpoint, and then click on this icon which says continue, or go to the debugger and type dbcont. That causes the code to continue executing until the next breakpoint. Now I may not want that breakpoint anymore, so I can click again to remove it. Next I can do db step out, or I could have chosen this icon up here that is labeled step out. Now where did that put me? That put me at the next executable statement after the function that I just executed. I can now continue to step through, or when I'm done I can just hit continue. Since I don't have any more breakpoints, that causes the program to finish executing. Notice that I no longer have the K before the prompt, so I'm no longer in the debugger. And there you see the answer, which is 1. In fact, let me just check again. Answer -1. That's the same error we saw before. Let me show you 3 more debugger commands that are very helpful. First, you notice here I still have the breakpoint set in quad simp, so I'm going to execute it again. I stop there. I will take one step, and then I want to step into simp. If I type db stack, that provides a traceback listing that essentially shows me how I got to this point. I'm in simp at line 11. That was called from quad simp at line 24. Secondly, remember I can look at my variables. This is in the local workspace that is inside of simp. Suppose I wondered how I got to this point, and I need to look at the variables in the calling function. I can do db up, and now I get to the workspace belonging to quad simp. I can look at those variables. I could even go up again. That gives me to the base workspace or the command window workspace, and I can look at those variables. When I'm done looking, I can go back down and back down again. Those commands, db stack, db up, and db down, are sometimes very useful when debugging. There are shortcuts for these commands in the Matlab editor. If I go to this drop-down menu, there I see the traceback listing. I'm in simp, above simp is quad simp, above quad simp is base. I can click on another function which essentially does db up, and go up again, and go back down. Now let's use the debugger to actually do some debugging. First I need to finish what I was doing before, so I'll type dbcont. That continues the execution to the end of the program. Now let's re-execute this command, except I'll change the name from quad simp to quad simp 1. I'm not debugging. And notice how long it's taking the program to execute. It appears that it's not executing correctly. Just for comparison, let's re-execute quad simp. I will need to remove the breakpoint though, because I don't want to debug quad simp. It didn't take any appreciable amount of time to execute. So there's apparently something wrong with quad simp 1. So let me put a breakpoint in quad simp 1. Let me execute it again. And let's see if we can determine why it's taking so long to execute. At this point, let's look at I1, a little more than 1, and I2. Notice that I1 is very close to 1, which is the correct value, but I2 really isn't all that close, 0.90. We continue to execute. Now I've recomputed I2. Notice it actually gets farther away from the correct value, not closer. Apply Simpson's rule again. Now remember, if I want to avoid doing that single stepping, I can set a new breakpoint and just continue the execution. And as I do this, I observe that the value returned by Simpson's rule is definitely not converging to the correct value. So this time through, let me step into the function. How should I debug at this point? One of the basic principles of debugging is that it's difficult to just read the code and find the mistake. Oftentimes when you're debugging, you're the one who wrote the code. There's a psychological fact that when you write something, you tend to see what you intended to write rather than what you actually wrote. For that reason, it's often difficult to find your mistakes simply by reading the code. At this point, we suspect that Simpson's rule is not implemented correctly. What I would suggest is that we work out a simple example by hand and step through the program to see if it's doing the calculation correctly. Now let's just look at the code before we design an example. I've got this preliminary part that checks to see if A is less than B as it's supposed to be, and then I check to make sure that I have an even number of subintervals. And then I have this loop, where each time through the loop I'm computing two function values and adding their contribution to the integral. Notice that the loop runs from I equals 1 to n over 2 minus 1. The simplest case would be n equals 2. In that case, the loop will not execute, and here is the value of Simpson's rule. So I probably want to check the result first with n equals 2, but then I'm going to have to use at least n equals 4 so that this loop will execute, and hopefully I can find the mistake. Let me show you another command. This removes all breakpoints from the files. I can finish the execution if I want. Now remember, the problem was that the code did not seem to terminate, so I'm going to use Control-C to stop the execution of the code. Now let me test simp1 directly. I'll use the same integral, first with n equals 2. I'm going to do the calculation by hand first. So I compute dx, and now I want to compute Simpson's rule. So Simpson's rule would say I use f of a plus 4 times f at the midpoint. Now the midpoint in this case is pi over 4, and then I have to add f of b. Now that quantity is multiplied by dx over 3. So there's the value. You might recognize that from when I was debugging, but just to check, simp1 f comma 0 pi over 2, 2, I get the same value. Now let's use n equals 4. I'm going to type out Simpson's rule with n equals 4. So f of 0 plus 4 times f of dx plus 2 times f of 2dx plus 4 times f of 3dx plus f of b is f of pi over 2. There's the value that I should get. If I run simp1 with n equals 4, I do not get the same value. So now I have localized the error. If I go back and look at the code for simp1, apparently this executes correctly because that is the output value when n equals 2. But the loop does not execute correctly, apparently. Now I only have to examine 3 lines of code to see if I can spot the error. And in fact, here's the mistake. I forgot to multiply this by 2. So if I save that correction, re-execute simp1, now I get the value that I expect. Let's do one more example of debugging. I have a function that implements Newton's method. I'm going to apply it to this function, f of x equals x cubed minus x minus 1. I've stored it as f5.m. Here's how Newton works. Remember, I have to provide a starting point. I'm going to use x naught equals 1 as a starting point. I'm going to display the results at every iteration. I'm going to go for an accurate solution, an error of less than 10 to the minus 10. I get 10 to the minus 16 as f top, and I'll use the default for the maximum number of iterations. Now that's the correct version of the function. As an example for debugging purposes, I introduced an error. This is called Newton 2. When I execute Newton 2 on the same problem, I get very different behavior. Let's go back to the output of Newton. How do I know that this is working correctly? Well, if I look at my output, I see in particular the estimated error goes from 10 to the minus 1, 2 times 10 to the minus 2, 5 times 10 to the minus 4, 2.2 times 10 to the minus 7, 4.4 times 10 to the minus 14. The error is approximately squaring at each step. Similarly, f of x, it's 10 to the minus 1, then 2 times 10 to the minus 3, 9 times 10 to the minus 7, 1.8 times 10 to the minus 13. And then we'd expect something on the order of 10 to the minus 25 or 26, but we don't see that because of finite precision arithmetic. We've reached round-off level here, and we can't expect to get a smaller value. Also notice that I am printing this convergence ratio. This is the ratio xk plus 1 minus xk divided by the quantity xk minus 1 squared. This ratio should converge to a constant. And we see that it appears to do so, converging to about 0.93. Now, in the incorrect version of Newton, well, the values of f of x are not decreasing to 0. The estimated error is not decreasing to 0. And these ratios, as far as I can tell, are not converging to a constant. So by every indication, Newton's method is not converging correctly. Let's examine Newton 2 using the debugger. First, I put a breakpoint in Newton 2. Then I'll execute the function again. Remember that if I use dbstop to put a breakpoint in the file, the breakpoint goes at the first executable statement. So initially x is 1, f of x is -1, and df of x is 2. So I can calculate what the next value of x ought to be. It ought to be x1 equals x minus fx divided by dfx. Should be 1.5. So there I compute the next approximation to x. It is indeed 1.5. I increment the iteration number. I compute the error. The step is 1/2. I went from 1 to 1.5. I'm not ready to stop yet because the step, which is the estimated error, is not less than the tolerance. The value of f is not less than the tolerance. I certainly haven't hit the maximum number of iterations. So now I need to prepare for the next iteration. I set x equal to x1, fx equal to fx1, dfx equal to dfx1. I print if requested, which it was. And then I start the loop over again. So here's x1. The new value of x1 is 2. Now is that correct? I should have x1 equals, x is 1.5. I have to type in the formula now for f prime of x. Get 1.3478. That is not what I got in the code. So there's something wrong here. Now, x is 1.5 as it's supposed to be. fx, I notice, is -1. F of 1.5 is not -1. So actually I have the wrong value of fx. Now where was that value computed? It was computed here, where I computed fx1 and dfx1, and then at this point I moved those values to fx and dfx. This is where the value was computed. And hopefully now you can see the error. Right here I was supposed to evaluate f at x1, not at x. So let me save that correction. Notice that Matlab does object to me changing the file and saving it while it's being debugged. But in this case, I do want to exit debug mode and save. So I do that. When I get back to the command window, I no longer have the debugging prompt. I have the ordinary prompt. I want to run Newton 2 again now that I've fixed the bug. Remember that I still have a breakpoint set in Newton 2, so I'm going to clear it using the dbclear command. I could also type dbclear to clear all the breakpoints. In this case, since I only have one breakpoint set, it doesn't matter which version of the command I use. Now I'll recall the previous command, run it again, and now we see that Newton's method behaves as expected. This completes my introduction to the Matlab debugger. If you want more information, I suggest Googling debugging in Matlab, and I think you'll easily find the documentation at the MathWorks website.